In algebra and precalculus, we learned a lot about how to graph functions. And then in the last few sections of calculus, we've also learned some other things about, say, for example, when the first derivative is positive, the function's increasing. And then if the second derivative is positive, the function is concave up, and those kinds of things. So in this section, we want to put it together. We want to put together everything we've basically ever learned about graphs and analyzing graphs from both pre-calculus and calculus into one handy problem with 9 steps. And we're going to use the computer, particularly I'm going to use Desmos, to graph that function and show all of those things on one graph. Okay, so let's start with the first things. We want to identify the domain of interest, of course, because if the domain or interval of interest is restricted, then we want to be able to know that and not graph things that are not worthy of our time. Now, the one thing to think about domains, oh, and by the way, this is a pre-calculus topic, right? But remember, what are the things you can't do, right? You can't divide by 0. Oh, I should say, watch out for, hold on, watch out for division by 0, logarithm of a negative, logarithm of 0, out for, so something divided by 0, any log of a negative, any log of 0, any even root, like square root, fourth root of a negative number. Those exist, they're just not in the real number system. And then, so they actually do have a graphical component, but we just are not dealing with it at this point. And then, all your trig functions, tangent, cotangent, cosecant, secant. Those are the ones that you have to watch out for because they have all sorts of places where they don't exist. And that would cause domain restriction. The next thing we want to talk about is exploiting symmetry. So there are certain types of symmetries in a function that we learned about in precalculus. Namely, if a function is even, that means that f of negative x is equal to f of x. The classic example of that would be an x squared function, right? Because it's symmetric across the y-axis. Sorry, that means symmetric with respect to the y-axis. Meanwhile, odd means that f of negative x equals negative f of x, which means it's symmetric with respect to the origin. So the classic example of that is x cubed, but of course many functions can have that property. All right, so these two items, in case you haven't missed it, these are pre-calculus. They're not a calculus topic. That's just a review of things you should have learned somewhere in your before calculus life. All right, now we have all the calculus bits. So we can find the first and second derivatives. They're needed to determine extreme values, concavity, inflection points, etc. So we would find the both the first and second derivatives. Sometimes the second derivative isn't practical, so sometimes you'll have to graph it without that second derivative, but for our problems we will be doing the second derivative. Then we're going to find the critical points and possible inflection points. So in our language, that's really the first order critical values, and the possible inflection points are the second order critical values, right? So where the first derivative is equal to 0 or does not exist, or where the second derivative is equal to 0 or does not exist, right? So those are what we have. So these ones are second order, these ones are the first order critical values. And again, the book uses the word points. I don't particularly like that because they really just mean the x values, but it's fine. It's very common lingo for calculus books. All right, find the intervals on which the function is increasing and decreasing and concave up and down. In other words, do the first derivative test and the concavity test. So this bit right here is the first derivative test. This bit right here is the concavity test. Not the second derivative test. The second derivative test is actually a test for increasing and decreasing. Actually, it's a test for relative mins and relative maxes. So we're not using that particular test in these. Then we're going to identify extreme values and inflection points. So that would be using the first or second derivative test, either one, if you want to classify the first order critical values. That would be looting there. So the first order critical values, both the x and the y coordinate of the maxima, minima, and inflection points are needed for graphing. All right, so this would be finding all your local mins and maxes and all of that good stuff. Right, so this is where all the calculus is. Right. All right, and by extreme values they mean local min maxes, right? And inflection points are obvious; those are the inflection points where the concavity changes direction. Next, we're going to find any vertical and horizontal asymptotes and determine end behavior, or maybe even slant asymptotes, if the case might be. Sometimes called oblique asymptotes, depending on what your pre-calculus book used. Right? End behavior, right? What's the limit of the function as x goes to either infinity, or the limit as x goes to negative infinity of that function. Stuff we learned about in chapter 2, right? So chapter 2. So do we have horizontal asymptotes or not? That kind of thing. Then we're going to find the intercepts. The intercepts would be, of course, where x is equal to 0 or y is equal to 0. And so if you're thinking, hey, those two things sound like precalculus again, you would be correct. Right? We did all of those in precalculus. Technically, you learned how to find horizontal asymptotes in precalculus. And then last but not least, we're going to use Desmos, but you could use a calculator, you could use other programs, but I'm going to use Desmos to graph this. Okay, so let's start with our example. So I have a function, and we're going to do all of those steps to this function, which is 10x cubed over x squared take away 1. All right, so let's begin with number 1, which is the domain of that function f of x. Okay, so for the domain, remember that we can't have division by 0. So that's going to be what we're going to look at to figure out where the values that are not in our domain are located. So we can't have division by 0, so I'm going to set my denominator equal to 0, and I'm going to solve this. Now you could factor it, or you could bring 1 to the other side and then take the square root of both sides. The only trick with that one is to remember that whenever you take the square root of both sides, you'll have to do plus or minus, because it's x equals 1 or x equals negative 1. Right, so those are the domain restrictions. These are things you cannot have. So your domain is negative infinity to negative 1, union with negative 1 to 1, union with 1 to infinity. This is the domain. In other words, it's all real numbers except plus or minus 1. All right, step 2, symmetry. Okay, so to figure out symmetry, you have to find f of negative x. And what that is will determine whether it was even or odd or whatever. Okay, so let's find f of negative x. F of negative x is equal to 10 times negative x cubed over negative x squared minus 1. Okay, well, a negative inside a cubed will actually become negative 10x cubed over, and the negative inside a squared will become positive x squared, because when you take a negative and you square it, you turn it positive. So in other words, this is negative 10x cubed over x squared minus 1, and that is negative, well, this whole thing really is negative f of x. Actually, let me write right here. Right? So I have the negative out in front right here. So this negative right here, that is the negative, and then the rest of it is my function already. So that means that my function is odd, right? So it's going to be symmetric with respect to the origin. So let me make a note. Therefore, f of x is odd, and therefore symmetric with respect to the origin. I'm not going to write those words. WRT. WRT, the origin. Okay, that part's done. Next, part 3. We need to find f prime and f double prime. Oh well, this is going to need quotient rule. So f prime and f double prime. To do that, let's start with f prime. I'm going to take f prime of x is equal to, I take the denominator, I square it, I take the denominator and I write it here, then I multiply it by the derivative of the numerator, which would be 30x squared minus, and then I leave the numerator alone, 10x cubed, and multiply by the derivative of the denominator, which is 2x. So that would be, let's think, 30x to the fourth minus 30x squared minus 20x to the fourth over x squared minus 1 quantity squared. And that would be 10x to the fourth, because these two are like terms. So 10x to the fourth minus 30x squared all over x squared take away 1 squared. All right, so then that's the first derivative, right, f prime of x. You could factor 10x squared out if you really wanted to, but there's no need because it doesn't really do anything for you. All right, then let's find the second derivative. So f double prime of x would be equal to, and then I've got to use quotient rule again. So I'm going to take my denominator, which was x squared minus 1 squared. I'm going to raise that to the 2 power. And then I'm going to take x squared minus 1 squared times the derivative of the numerator, which is 40x cubed, take away 60x, minus, let me bracket there. Now I'm going to leave the 10x to the fourth minus 30x squared alone. And then I'm going to multiply it by the derivative of x squared minus 1 squared, which would be 2 times x squared minus 1 to the 1 times the derivative of the inside, which is 2x. And that's your second derivative. Now there's some ways to clean this up a little bit, just in case you were wondering. This is a lot. And I know you might be thinking, oh, we should distribute out that x squared minus 1. The answer is, not necessarily. So this is x squared minus 1. Well, let's see if you can see it. There's an x squared minus 1 here. There's actually 2 of them. And there's another one over here. So what I can do is I can factor that out, right? X squared minus 1 right here. And then that would leave me in this first term an x squared minus 1 times a 40x to the third take away 60x minus, right, there's a 4 here. 2 times 2 is 4. So it's 4x times 10x to the fourth take away 30x squared. This is all over x squared take away 1 to the fourth, because 2 times 2 is 4. That would be, okay, well, I have an x squared minus 1 here, and I have x squared minus 1 to the 4 here. So this one x squared minus 1, because this is multiplied by this whole thing, oops, I forgot my bracket over there. Because this is multiplied by the whole thing, I could cancel one of them out and just make it x squared take away 1 to the third in the denominator. And my numerator will become 40x to the fifth, I'm foiling, 40x to the fifth minus 60x to the third minus 40x to the third plus 60x, right? In other words, I'm distributing, right? Minus another 40x to the fifth, oh, look at those will cancel, plus 120x to the third. Oop, that's a 3 over there. Right, all I did was distribute. So I canceled out one of the x squared minus 1s, right? I turned this 4 into a 3, and then I distributed 40x to the third times x squared, and so on. So distributed these two, and I distributed this one. And then I'm noticing there's some canceling going on here. So I can, or subtraction, right? So 40x to the fifth minus 40x to the fifth is gone. Let's see. Combining like terms, the negative 60, the negative 40, and the positive 120 are all like terms, and that would make 20, right? So it'll be 20x to the third. And then plus a 60x all over x squared minus 1 to the third. There's the second derivative, simplified. Right, so here's the first derivative, simplified. I mean, technically the first derivative is this part right here when you first do the quotient rule. So there's the first derivative, but then we're simplifying it. So there's the first derivative. Here's the second derivative. Right here at this step, we found the second derivative, but if we want to simplify it, that gets us here.